All right, hello everyone. Let's go ahead and get started. Thanks so much for joining today's webinar, Making It Moldable from 3D Printing to Injection Molding. We're so excited to talk to you about strategies for producing high quality injection molded parts, particularly through the lens of after you've done some 3D printing prototyping. So first, I'm Serena and I'm on the marketing team at Zometry. I will be facilitating today's webinar, so at the end you'll have a live Q&A session and I will send your questions to our panelists. So a couple quick notes before we get started. Please submit those questions throughout the webinar in the question box for your panelists to answer at the end during the live Q&A. And after the webinar, we'll be sure to send everyone a recording so you can rewatch this webinar or send the on-demand copy to share with your colleagues. And at the end, we'll also have a special discount code for you to use. Now I want to introduce our first presenter, Greg Paulsen. Greg is there he is, the Director of Application Engineering here at Zometry. He's spent over a decade working with engineers on custom manufacturing projects using CNC machining, additive manufacturing, sheet metal, urethane casting, and of course, injection molding. Prior to Zometry, Greg worked in product development with a focus on ruggedized electromechanical systems. Next is Kyra Stawson. Kyra is our technical sales engineer for our injection molding division here at Zometry. She graduated from Penn State Behrend with a degree in plastics engineering and has a background in automotive manufacturing at Toyota. Her passion lies in the design stage of injection molded parts, which makes her a super valuable asset to us here at Zometry to help customers like yourself take projects from start to finish. And lastly, we have Kyle Adams. Kyle is a senior injection molding engineer at Zometry and has 14 years of rapid manufacturing experience, including quick turn prototype injection mold tooling from his time at Eccentric Mold and Engineering and 3D Systems. He excels in consulting on your projects to deliver parts for a variety of industries and specific end environments. So with that, thanks again for tuning in, and don't forget to submit your questions in the webinar question box. I will pass it over to your injection molding specialists.
Hey, Serena. First off, Serena, thank you too. Just so you guys know, Serena is behind every case study, a bunch of the articles you see, and of course these webinars as well. Like she makes it happen. So I keep on saying we need to add the Serena bubble at the very top here, give her own page. But it is really exciting to be here, and it's really exciting to talk about injection molding, especially with this team. If you've already dabbled with injection molding with Zometry, you may have already had a couple conversations with these folks already, but just a great talent pool and great communicators when it comes to mold design and some of these injection mold principles. So yeah, today we're going to be talking about making things moldable. So we are focusing primarily on that effort where you may have gone through some 3D printed prototypes or may have had a design that you've done in some small scale, and all of a sudden your demand has risen and you need to make this into a scalable, moldable product. And we're going to go through a few design examples, as well as just talk about injection molding in general and why it's so specialized and why it's so design dependent as well on the outcomes. Our brief agenda here, we'll talk a little bit about Zometry, what we do and how we work with injection molding, go over some of those principles of molding, and then we'll go through specific design examples. One thing to note before I get into this is that if you have any questions, please add those to the questions tab. These are professionals, including myself. We've done, over, decades, or probably combined like 30 years of answering questions on these subjects. We love answering your questions about molding, about manufacturing in general. We're here to help. So yeah, speaking of that, Zometry, we make a lot of parts. And Zometry is this go-to one-stop shop for on-demand manufacturing. We work with your design. You upload it to our website. You'll get instant pricing and lead times in a majority of our technologies. That's 11 different manufacturing technologies. And then you will basically have a checkout experience like you're buying from Amazon.com. It's a very clean checkout experience. With your quote, you have access to our team of professional engineers and experts. We're able to help work with you based off your time, scope, and cost as well to help determine your schedule. And we make this all just very simple, very single storefront, web-based experience for you. The platform itself allows you to configure your quote even further, so get detailed specifications, get some manufacturability feedback, and again, that pricing, those lead times show up automatically. Ooh, I'm getting some updates on my site here. So we guarantee the quality and timeliness of your parts. The way that we do this is really unique. We actually have a marketplace of professional manufacturers distributed across the US that we have vetted through Zometry's online platform. So we have shops that are small and large. We have machine shops. We have tool and die shops. We have 3D printing bureaus. And we're able to match the needs of your work. So what makes your project most successful with those manufacturers that are best able to complete that. When it comes to injection molding, that could be a bridge tool. So shops that like to do these lower volume bridge tooling designs. That could be prototype tooling, or that could even be full-scale production tooling with the gamut of qualification needs that you need to make your project successful. We have this diverse distributed network that we have access to allow us to take on multiple projects at a time and multiple projects in parallel for you. So we can really do a lot of work, not just from the diversity of experience, but also concurrently for your project needs. And these, again, this goes down to machining, sheet metal fabrication, plastic and metal 3D printing options. In fact, 3D printing, we have 7 different 3D printing technologies available. So if you've used us for 3D printing, you may have seen that gamut there. Urethane casting, and of course, injection mold services. So today, though, it's about molding, and we are happy to talk about it. So I'm actually going to bring Kyra in now, talk a little bit about this experience with molding with Zometry. And Kyra, what makes, first off, why would I choose molding? And then, what makes molding with Zometry such a good experience? Oh, Kyra, let me get you.
Okay, can you hear me now?
I got you. Okay.
Okay, sorry about that.
I think we were both clicking on mute at the same time there, so it's like a door lock incident.
No worries, no worries. So yeah, like Greg said, we are talking about injection molding today. As Serena noted before, my background is specifically in molding. I've studied it for several years now, with some background in automotive and everything like that. But I'm happy to bring my experience here and discuss with you guys some general tips about molding and everything. So all in all, injection molding is the cheapest process, for a high volume run of parts. Over time, given a simple cost analysis, you'll see how it compares to, a process such as 3D printing or something else that we may offer on our platform as well. It is the most consistent and reliable process over time as well. It is the most repeatable in regards to holding tight tolerances, even of the nature that you don't have to have an operator or anybody standing there for every different cycle, depending on the part complexity and geometry as well. So, all in all, it is a repeatable, at high volume, scalable process. Even mid to high volume. I know here we offer some low run production tool, or excuse me, prototype tools as well. Just to, if you need to have the certain material requirements or properties that you need to test for your application, or just, want 100 parts here and there, we are happy to provide a solution for that as well in regards to molding. So, as a process itself, it is the highest variety. It has the highest variety of materials, colors, configurations, anything out there. If anybody has experience in molding, you understand that there are thousands upon thousands of different materials available in the industry. It just depends on what your application needs and, different properties that you require for that application as well. So, and then on top of that, even farther, what you want your part to look like. So everything is customizable. It depends on, the application itself, what you want the part to appear as, whether it's bright and glassy or maybe dull and matte finish, whatever that may be. Molding is the most customizable solution for you in regards to an end product.
Yeah, and I just, I'm getting a little bit ahead of this, but one of the most common questions is, do you mold X material? And our answer is almost always yes, because we are actually sourcing these materials specifically for you. And I know I'm segueing into that, but that is a question I get very, very frequently is, do you mold X? Yep,
Yeah.
yeah, we do.
Absolutely. And that kind of steps into our have it your way approach. So with the material, we don't have any material limitations. As long as it's available in the manufacturing location, we are able to source it. There should not be any issues there. We are not limited to what's shown on our website. We can source, just about anything to fit your needs. So that is definitely a privilege that we have and definitely take pride in. But along with the have it your way approach, there's really no design limitations or anything or restrictions that we have in place either. All we want to do is help your part be more moldable, and we want to get it as close to your design intent as we can in regards to producing a part, to make your dream come true, essentially. So we do offer, I know that's a little bit cheesy, but it's true. So we pride ourselves in taking it from start to finish. So we do offer long-term solutions and not just prototyping as well. So if you do scale up at a very high rate, we can offer those services too. Just taking it from, a design intent, like I was saying, to 3D printing, to now low run injection molding to get all the bugs out. And then we can also support the high run volume as well. So another benefit about Zometry is communication. As you can see, engineers are readily available, including myself. I've been on several customer calls and, even presented a lot of quotes for, some people that might be on this phone call as well. So we've probably had a chance to discuss your project too. So communication is definitely something that we, strive to always be the best at. We want to offer all of our resources that we can, and we'll always be a resource to you and help you along the way with your design. For initial quotes, we do turn around those in about 24 hours, give or take the complexity of the design as well. We offer DFM feedback with every single project out there, especially, we have conversations up front, but, when you do place your order with Xometry, we offer a formal package addressing any concerns or anything that we may have missed on the front end, and that is standard with every single order, including, a flow analysis as well. So with Zometry too, we do have a large partner network. We have thousands of partners across the globe, primarily here in the US, but as well as international overseas. So we can default to either one, depending on your restrictions, or, if cost is a factor, then of course we might want to sway one way or the other. So we can do that to fulfill your needs specifically. And the benefit beyond that is you don't have to learn any languages or anything like that. We are the only point of contact for you. Xometry is the manufacturer on record. So we handle all of the communication with our partners, make sure that, there are no delays. If there are, for whatever reason, you will be notified, but you are only speaking to Xometry. So we make that very simple for you. What we say is we actually provide, a simplistic factor for you in regards to having your vendor, but we are really flexible with our capabilities because we do have so many partners in our network as well.
Yeah, I think the term that we talk about a lot is the white glove service when it comes to the manufacturing, because we do have the expertise in-house. So we're working in-house as well as managing some very, very talented manufacturers across our network. So it's really the best of both worlds. So you have someone that you could just call and contact. And I know Kyra mentioned this, but you have that direct point of contact as well. So from any quotes, even if it's a 3D printing or if it's injection mold quote, you'll have a direct sales contact that you always reach out to, and they may bring Kyra in for a call, or bring Kyle in, or some of our other talented engineers for things like DFM feedback and consultation as required. So one of the things, and speaking a little bit about this with Kyle earlier, is we're about to go into design. My experience has always been kind of know the process first, and it's going to help you get more intuition about why these design principles are needed. And yeah, so Kyle, we have some slides set up here, and I was wondering if you could walk through just some of the basics of molding.
Absolutely, yeah. So obviously the biggest thing is to understand, have a knowledge of what is going to happen and when it's going to happen, so that you can be informed of the whole process, whole step. So every tool is cut, every tool is designed, is as Kyra mentioned, to your part. It's not an off-the-shelf part. Everything is custom made, and it's not just to your part. It's also to that specific material. So, with the thousands of materials, essentially you could have several different options in your tool requirements. So Tools cut, obviously part of that process, when the tool opens and closes, you have that molten plastic that gets injected in there at high pressure. Again, material limitation dictates a lot of that. The part itself is injected quickly, but then it has to cool quickly at the same time. Otherwise, that part can't get ejected without causing damage to the part. And then when that part ejects, it usually falls onto a box or maybe falls into a conveyor belt, or in the picture here, you have robots that'll actually pick it off. So every part would be a little bit different in how it can actually get removed. Parts themselves, geometry themselves, again, kind of go back to what Kyra mentioned, there's no real limitations to it. A lot of the features that are not captured in that direction of pull are creating undercuts, and those are created using slides or sometimes hand-loaded cores to help kind of capture those features on the part itself.
And I got the little thing here. I'm gonna skip
ahead
on.
Perfect.
Like 1, 2, 3.
Perfect. Yeah. So as far as the molding operation itself, this is obviously a nice little representation of a press itself. So, 1, 2, 3, 4, as you see there. So the first step itself, you have that hopper. The hopper at the top is where you're actually putting the plastic. Material goes in there in that pellet form. It's fed through the hopper at the beginning of the number 2, which is the barrel and the screw itself. So there's a screw that's rotating, just turning and turning and turning. And as it goes along, it's actually heated up at the same time. The picture actually shows 3 little bumps at the very top. Those are actually like heaters. That actually is what heats the material up as it turns and plasticizes the actual material itself. So as it's brought up to the front, which is where the tool is there, that's where it's then injected into that core and cavity side of the tool to help fill the part. As I mentioned earlier, it's injected into the tool. It cools down, and then once it cools, it then usually will drop into a bin or the conveyor, or again the robot will actually reach in and pick the part off with the runner involved at the same time.
So when we talk about this and we talk about why everything around us right now is injection molded plastic, but like what is this 1, 2, 3, 4 cycle? Like how long is that usually when we're making parts?
Well, I mean, from the time the material goes in there to the time that the part hit the barrel, it could usually be a few minutes. But the actual, call it step number 3, it could range from 30 seconds to 2 minutes. It really depends on the part. It depends on the geometry of the part, the material. There's a lot of key factors that kind of play into that cycle time.
All right. So, and this becomes important because I know we have some other things talking about like what adds the cycle time, because that really is that's a measurement of throughput, right? So like how many can I produce per day, and what can we do to make more parts with that? So
absolutely. Yeah, and there's a lot of terms you're going to hear. I mean, not just from us, but from anybody. You have single cavity tools. Obviously, single cavity meaning one part. So every time that mold open and closes, one part's going to pop out of that tool. Family tools itself, it's a good, easy way to maybe keep that tool price low. Sometimes you can put 5, 6, 8 designs into one big tool. Sometimes you can't. It just depends on the geometry. But it's, again, a good way to put all designs into one tool. If it's different sizes, you may have to have a runner shut off, so only one part will run at a time. So you're not really necessarily saving on your parts, but you would be saving on the tool. Multi-cavity tool, so again, if you're going into high volume, if you're needing call it hundreds of thousands or even millions of parts, you're going to want to look at high multi-cavitation tools, 2, 4, 6, 8, 16. I mean, there's a lot of variations on what can be done with these multi-cavity tools. As I mentioned, the side actions or slide, those again it's a mechanical component that actually captures holes in the side of the part. That's not something that's captured in that direction of pull. Gating, again, that's kind of where material itself is actually injected into the tool, into the part itself to help fill it. That vestige that's left over is used, that little piece of plastic that's hung out on the part that has to be trimmed to leave you a nice finished flush part. Ejector pins, Usually it's circular, but it doesn't always have to be round. Sometimes there's different plates or different blades. Sometimes you actually don't see any marks on the part because you're actually ejecting off of hand loads. You're actually pushing the hand load and it's actually removed all by hand. It just depends on the part. Parting line, it's that visible seam. So everywhere that part opens and closes, the tool opens and closes, that's going to be that visible mark from that parting line. And then the shut off is actually where, again, the tool itself would shut on itself.
Yeah, and just so you guys know, like, so some of these things like parting and shut off are often dictated by the CAD geometry itself. When we're kicking off a tool, we usually discuss that peg, right? So parting, ejection, and gating. We talk about where you should expect to see that. And something I've always noticed is gating usually is, if it's not an edge gate, which is going to be like right on the kind of the parting line. Gating is usually on somewhere on the pretty side of the part, and then I usually see those ejector pins on what we call the ugly side of the part, which is not usually ugly, but it's usually the one that's non-cosmetic. So like you have the outer side of your housing, then you have the inner side that's holding your PCBs and stuff together. Just I actually always have this question, like why is gating always or usually on the cosmetic side of a part? Why would I usually see that?
A lot of times that's just because of the actual ejection side of it. The ejection's always on that core side of the tool. The gating is always on the cavity side. Again, we try to do our best to put that gate into the least cosmetic of the cosmetic side, to try to hide it. And back to that peg discussion, we always usually have that conversation with you ahead of time of where can we put that gate. We're not going to just put a gate on a part without running it by you. Yeah. We want to make sure that it's something that is approved on our end and your end, so that we don't have to discuss it later on and try to fix it.
And at the same time too, sorry, Greg, at the same time, it's important where the gate goes, because it depends on how your part fills. So it's very critical on where it goes as well, in regards to what you want your part to look like afterwards. So one, it's critical with how the material flows, and two, it's ultimately your discretion whether you approve of the location that we choose first and foremost.
And I know we have this question a lot too, especially when we're talking about that prototype or bridge tool versus a production tool. So we made this little graph, but like, just when would I choose? And then first off, what are hand-loaded cores first off versus automated slides? But why would I choose either? Or like, what will we do to help recommend the right approach for you?
So a lot of that will depend on how many parts you're actually going to need during your run. If you're needing hundreds of parts at a time, hand loads could actually be a better benefit for you. But if you're looking for, called a true production, you're needing thousands of parts at a time, maybe need them, quickly at a certain time frame. That's where maybe the more automated slide would come into play. As far as what a hand load is, in the picture, actually a pretty good depiction there of loose pieces. That's really what it is. It actually is a loose piece that actually gets sort of fit into the tool, and as the tool opens, that loose piece is kind of stuck onto the part, and an operator will actually stand at the press and remove that hand load, which is still part of the part, out. It's then taken off the part and then installed back into the tool. So the hand loads, it's a good benefit for low volume kind of tools. It keeps the overall price of that tool down. But obviously with the operator having to stand there, it does drive that labor price and labor cost up. And it takes longer, so the output actually goes down, your daily output. Usually you can do, call it 300 to maybe 600 parts a day with hand-loaded tools, because you're also only able to run that when you have operators on staff. And automated slides on other hands. Go ahead.
I was going to say something to note on hand loads too is oftentimes, depending on the throughput and the actual, like, how your estimated weekly volume or whatever your estimated needs are, there actually may be multiple duplicates of those hand loads, so that a part is removed. Those hand loads are being manually removed from the part that was just made while fresh hand loads are put in. So oftentimes there's at least 2 sets where one is, being removed while the other one is running hot on the press.
Good point. Because yeah, you may have 5 or 6 of these hand loads, and by the time it takes you to remove all the hand loads from the part, I always kind of consider it like Jenga. You're delicately taking the part and the hand loads out. You don't want to have that press just sitting there idle doing nothing. So you do have the extra pieces operating at the same time. Just kind of wrap up. Yeah, the automated, obviously, that the tool price is going to go up because you have a lot more mechanical action in the tool itself, but you're not having an operator stand there, so the labor rate goes down, and then your output goes up, because then you can run that tool in a lights out situation overnight. So you show up the next day and there's a box full of parts sitting there ready to be shipped out.
That's awesome. So all right, so just reason why we want to bring up like the tooling and the tool approaches, because you're going to be flowing this molten plastic into this cavity, and this cavity is in the shape of your part. A lot of weird things happen when plastic flows into parts and then cools down. First off, hot plastic is expanded. Cooler when it cools, it shrinks down. So when we talk about design for manufacturability, a lot of that is around that plastic and how to mitigate some of these costs, including what Kyle's mentioned with hand load stuff. And we have this molding trinity that Kyra has emphasized over and over again. So Kyra, I'm going to let you take it from here, but this undercuts, uniformity, and drafts.
Sure. Yes, this is, if you want to take anything away from this phone call, take this away. This will help with all of your designs. It's applicable to every single injection molding design out there. Any part you can buy off the shelf, any part you'll see in a car, any part you'll see anywhere, all of these 3, analyses apply to that. So what you're seeing here on this image is just basic 3 analyses that we do and we offer with every single order that we get through our molding department here at Zometry. So the first one is thickness, that you're going to see in the little checkbox down there. This is just a snip right out of our DFM feedback that we offer to you. So thickness analysis, undercut analysis, and draft analysis. We identify those, and then, no, you're fine. And then we identify the overall moldability of the part. So the first one, like I said, actually in a different order here, is undercuts. So what undercuts are is basically a feature that is perpendicular to the parting line or the direction of draw. So you can see in that first image, it's that red circle. Same thing what Greg is pointing to there in those red faces. You can see that we've done just a basic undercut analysis on that blue face, and it calls out everything that's in the opposite direction, essentially. So what that means is, like Kyle said before, either a hand-loaded core or side actions are needed to form those features because they're not captured in the direction of draw. So, and those, we aren't limited to those whatsoever. Zometry can absolutely handle, most side actions and undercuts out there. That's no problem. But we do encourage you to, evaluate your design, eliminate any if unnecessary, just because they do add some cost to the part. And of course, we want to make it most cost effective for you. In most cases as well, like I said, they are achievable. However, in some cases, a die lock condition is encountered where basically there's 2 different side actions kind of going together in different locations, and you can't really pull them out at the same time. So it kind of creates like an intersection where they're kind of locked in place. So that's what a die lock is. And that is not achievable with those standard actions that we talked about. So that is something you wanted to avoid. And then, of course, whenever you're doing these analyses, you can see where all the red marks kind of show themselves and reveal where you're having an issue. So it's kind of the benefit with the software that we use and we have here in-house. We can call all of that out, and yeah, there's really no limitations there, like I stated. So the best practice would be to minimize those, like I stated before. 1, because it does reduce the cost, and 2, it just makes your part a little bit easier to be moldable. And then something that's really awesome that we stress a lot are pass-through cores. So you can see that last image there, there's that slot under that snap fit feature. We encourage you to design that in because now that design can be captured in an open close method. There's no side action required if there's a hole there. And that's what Greg's pointing to right now. So yep, that is very helpful. There are a lot of tips and tricks, and that's what our communication here offers, because if I see that, I can directly point that out to you and let you know how that could be more beneficial to your design.
Yeah, and I always think about, imagine shining a flashlight up or on each side of a part, and if there's a shadow somewhere, That means, so if you have, then that means that you have an undercut, and that'll either have to be, well, it'll always have to be approached by adding some sort of slide or core in place to do that. So some of these fun things like just adding a slot, all of a sudden I can shine a light through and the beam hits the bottom of this piece, and now I have a 2-part mold versus a mold that requires a slide, and I just saved myself a bunch of money. So it's a really good way to save costs on your injection mold design, is by mitigating as many undercuts as you can. And there's some really great tips out there, including some of the stuff in our design guides.
Yeah, and number 2 here is uniform wall thickness, or also known as uniformity. The unwritten rule that everybody should know in injection molding is maintaining a uniform wall thickness across the part. This is critical because if this is not achieved, it can result in 2 defects. One is sink, and the second one is void. So you can see the image here to your right, I believe that would be the same side there. So the pour design at the top, it shows a really thick section right there in the middle. So one that can result in a sink, like I said, a sink is just a minor indentation on the reverse side of the part that just shows, kind of reflecting the features on the opposite side. So you can see these in your common like plastic totes or garbage can or whatever in your house. They are present there. They are not detrimental to the function of the part whatsoever, unless it's very significant, and I'll get into that a little bit. And then on the contrary, you can either get, like I said, a sink, or you can get a void, which is just either air or gas trapped in the middle of the part. This can be detrimental to your function, because if it is gas and your part is later exposed to heat or anything like that, it could expand and then show through. So that's obviously not good. We want to mitigate that by coring out that feature, as you can see the improved design underneath. So that is what happens there. And sink happens because basically what it is it's your material shrinking together. It's pulling away from that surface because there is that big thick section there. So like I said, if it is significant enough or severe enough, it could cause warp, which could be obviously detrimental to the function of your part as well. So like I said, in order to mitigate those risks, we want to, reduce the thickness of those areas, core out the features. You'll see that as well along this part that we have here. So the last check that we want to do is a draft check. So what this is it provides ease for ejection. And we do that by just applying a minor angle to the outer walls of the part, as you can see in those images too. So we need this to release the part from the tool because it creates a vacuum and it's really hard to pull off without it. If it's not there, it could result in drag marks or scratches to the surfaces of your part. And we obviously don't want that for your design. Ideally, we like anything above 1 degree, just because that is, more the better. But at Zometry here, some features we can get as little as a ½ degree of draft. But again, more the better. And you can see in the image that all the yellow surfaces on that leg there require draft. It either should be red or green.
Yeah, and in this image, by the way, so a lot of these analysis, the good news about this is they are available in most professional CAD platforms. So if you're already designing in SolidWorks or Inventor, you're going to have access to at least that undercut check, draft checks, and there may be a thickness analysis. So if on these images here, those are basically taken from a standard edition of a professional CAD software. We highly recommend using that as frequently as you can when you're in the design process, especially when you're taking something from a 3D print to a mold, because thickness is going to be one of those first things you're going to be like, hey, I don't need all this extra mass anymore, because you're not going to be changing infills and stuff on your part, and it's very easy to assess. Our team takes a further step, and we do more sophisticated analysis as well once we move into a finalized DFM on the part here. But I did want to say, like, these tools are common. A lot of times it's just knowing where to find them in the Evaluate tab of your professional CAD, but super, super useful to know where to check for those. Mm-hmm. And this is kind of a putting it all together. So, on this actually design is a little drone leg that we use, and we print a lot of these here. But in this case, you're checking undercuts, and you're kind of looking at both sides, and you realize, this is going to be a good center part. So if you imagine the tool closing and creating both halves on kind of cut into the tool, and then this feature here would be created using a slide or side action to it. But some of these, this part was put on a diet. Some coring's been made to remove remove some material, and all of a sudden your design's that much better for molding. And one of the things we want to emphasize is we can inject plastic into your original shape, but the outcomes, the outcomes of that are, really large dimple type features from that sink, and there's a lot of outcomes that we don't want you to do. Our goal is your success. So so when we're talking about these design considerations, it's not a critique of the model. It's us thinking about those outcomes, like the future outcomes when we're molding these parts. So this is a stage here. So please, I see some questions coming in. Please make sure to ask some questions. We're getting close to the Q&A section here. I'm actually going to go through a quick little example in CAD just to show you how this process may work, and kind of getting a foothold, like a foot in the door on moving a design to injection molding. And I know we have a couple of design tips as well to go through. But we're going to have Q&A right after this. So this design is a simple case. It's going to hold like a PCB in the middle and has a lid to it, and it's pretty chunky. It's designed so it could be 3D printed. So like think like a 3.5-inch case, or you can even machine this design because it has big broad radii to it. But it's designed for FDM 3D printing. So when I run an analysis on this, I'm going to very quickly see that, I have some really thick, uneven walls here. If this was just straight molded, you would find sink almost to the point of deformation of the part. Like the pool of the sink may actually change the geometry of the overall geometry and function of the part. So what you want to do is start thinking about how can I turn this into a more even wall thickness. Again, this is just the beginning. Like this example here would be, hey, I have this part, I've made a dozen of them, now I need to make 700 of them. So like, how can I get from that, dozen to 700 parts here? So one of the first things I may do is take a look at what my functional side is. In this case, I have everything attaching from the top here. So I want to think about how can I remove material from kind of the non-cosmetic or non-functional face. In this case, I ran a simple shell command. So running shell across this all of a sudden gives me an even wall thickness across the entire part. And, I'm like already halfway there and making a part that looks, moldable. When we talk about the next steps, it's about looking at my draft. So when I could do a very quick draft analysis, take a look and realize that, hey, right now, I have 0 degrees on my pool directions. I have already done this, as you can see, because in SolidWorks, I'd probably crash the computer if I didn't do this beforehand. But, I've used a draft wizard and some manual additions here, and it's just very minor. But now I have draft in the pool direction so that this part will appropriately release after the tool's closed, plastic's cooled. Now, the second that it just moves a little bit, I have an air gap between my part and the tool that helps it release successfully. So applying that draft is very important. The other things that I took a look at, so I do have this part. It is on a diet. It's got even wall thicknesses. A lot of times you want to stabilize a boss or a protruded feature like that. So I added a rib command, and now I just have a little bit of stability on these, so that since this is the install point, I may have I may need that to be a little bit more rigid, especially if it has something installed to it. And then the last thing that I have is adding some fillets, which, just like draft, help the release of that part. So in some very simple steps, I've taken something that would be very difficult to mold initially, and I've taken this design and brought it to a point where I can do some limited scalability via injection molding of this design. I'd really like to show this example because it is something where it starts that mentality. The next steps of this is I may go back and take a look at this and really critically think, do I need 6-tap tools? Do I need do I need some of these external faces, or was it just convenient to grow this without supports this way? And you could start thinking about how your design may change and be optimized even further for molding. but this design here, just some very simple things like using those shell commands, adding those drafts and some ribs when needed, especially across chord areas where you don't want to reduce flex. So adding some ribs for stiffness versus adding mass for stiffness are just some huge improvements on the moldability of your design going from 3D printing to injection mold.
The other thing, Greg, is it's obviously moldability is one thing, but you're also saving money. You know, you're removing a ton of material, and you're also removing a ton of cycle time by doing that core out, which that's usually what people care about the most sometimes.
Great. Yeah. All right. So yeah, and I was actually, Kyle, did you want me to run through this, or do you want to run through some of these tricks here?
Yeah, you can go for it.
I have a couple more tricks of the trade that we've learned along the way. So one of the things we're talking about is a boss is essentially this extruded column, usually accepting a screw to it. So, you know, some sort of threaded feature. Sometimes it's accepting an insert as well. One of the things that's very common with boss design is you see a see-through kind of like donut shape impression on the other side once it's molded. This boss trick, I wish I knew it years ago. I know it now, and it's an exciting little trick here. But if you think about this as your nominal wall thickness, if you go about 30% down and do about a 30-degree cut and essentially have kind of a rotate cut around your feature here, what this does is actually it tricks the sink, if you will. So the sink would right now the mass from this column would be pulling from this wall here, but by kind of making this little cut, it actually will significantly reduce the amount of stress that's pulling on the cosmetic face and reduce that type of O shape to it. So actually a little tiny cutout ring around bosses can be very, very good for reducing that see-through sink. Again, if it's my workbench, don't worry too much about it. But if it's a design like a external cosmetic case, it could be a lifesaver, especially when you're adding that integration into your design.
Hey, Greg, I actually have an example here. I can try and show if it works for you. I'm not sure if I can. You can kind of see the outline of the ring there.
Yeah, so you see, and this is something also we're talking about mold texturing. High gloss items you will show everything. You know, they will reveal all. So ribs and even everything that's specifically designed. If you know on the first run you may still see a very fine sink line, which if you start looking around at parts all around you, you're going to see some of those very fine sink lines. So again, it's not affecting the mechanics of the part, but it is just something to be not aware of.
Right.
And yeah, even like at the very beginning, we had that blue part there. That blue part has a mold texture. I think it's like an MT1020 mold texture that was applied to it. But there actually is a slight ring, but because that texture is there, you can't see it unless you're holding it right at the right light. It's almost invisible because just by changing the texture of your tool surface and that transfers to the part, you all of a sudden are like hiding some of these cosmetic variations. One of the things we get asked a lot is, do we do insert molding and overmolding? Yeah, we absolutely do. And what's cool about us is we're also a machine shop or a sheet metal fabricator. So we oftentimes will also mill the insert. So a stainless steel insert for a strain relief with a TPE overmold is something that we can actually do the whole kit and caboodle. So we could take an off-the-shelf item, overmold over it. We can custom manufacture that item, or if it's a non-electronics item, we could also take your mechanically provided item and create a tool to overmold on those. I know we also do overmold projects, so that would be where you make typically a rigid shot first, and then you do a secondary shot. So think a toothbrush handle around that. And I just know there's some chemistry behind that as far as adhesion, where you have to build some mechanical design sometimes for adhesion. But yeah, ABS plus TP is very, very common there. And we can answer some more questions about insert and overmolding as well if you have them. But I did want to get to some of these questions that we have. Other considerations is if you have external threads are one of these very interesting designs where a male thread can actually be molded if it's with like kind of right on the parting line. So you can actually do an undercut analysis and look on each side and find that actually it's very forgiving for doing that. Something to notice, you will find a small parting line here when you're molding in threads. Not too bad with coarse threads, but finer threads, sometimes you may want to think about doing a very fine cut on the place where it's going to part, so that that those threads do not interfere with their mating component. There's some cool little tricks that you could do there. But if you ever look at some of these molded threads and you see two flat sides to it, that's actually a trick to help mitigate any interference with that parting line. And going back to kind of inserts and hand loads, I know Kyle I'd love to hear on this, but my assumption right now is that if you're doing something low volume and I have a female thread, that I'm using usually a hand load to cover that, right? So versus like unscrewing a system.
Yep. Yeah. I mean, again, that could be ejected with the part and then manually just unthreaded. So like the gray and the blue parts there in the picture, those could be formed by just a simple unthreading action of the part and then put right back into the tool.
Awesome. All righty.
So, real quick, I guess, Greg, to maybe tie into that, some of the inserts. So the other side that we have to consider a lot of times is if it is just say a brass insert. A lot of times we may see designs that have 15, 20 inserts, and we don't always want to insert mold those just because of the time it takes to physically load each insert onto the tool. The other great thing is that we're not limited to one process. We can do heat stick insert as well as inserted inserts, overmolded inserts.
All right. Okay, so let me go here. Yeah, sorry about that. All right, so just something to notice, by the way, if you have any questions that you want to talk to us about, support@zometry.com is the go-to catch-all email. And even if you have a dedicated account rep, if you go to support, we're going to make sure that you get in touch with that. If it's an engineering, a pre-sale engineering question, even a case management or post-sale question, this is a great place to go to. The same with that phone line. We have engineering support available from 8 a.m. to 9 p.m. Eastern. This is everything. This could be anything from your specific quote to just troubleshooting or FAQs. And even on our website, we have some great chat engines. And of course, our FAQ system is actually linked with chat. So if you ask a question to our chat, you will actually be able to see some links about some other information, like getting to design guides or getting some materials questions answered for you. Speaking of design guides, zometry.com/resources, some really great design guides. So if you are taking a file that you've been producing another method, looking at moving to molding, highly recommend checking out our design guide for injection molding. It goes over some of these things we talked about in much more detail and some specific measurements and guidance as well. Serena, is this the updated code? I'm going to put you on the spot here, but I just want to make sure. Do I have the? Is this right? Yeah, awesome.
So, just to let you guys know, we offer $500 off your first Xometry mold order. This will be valid for 2 months, and so please, follow up with our injection molding specialists and make full use of this.
That's awesome. All right. Thanks, Serena, for that. Yay, new mold order. And yeah, I think it's time for some Q&A. So happy to answer any questions. And I know, do we have some lined up? Awesome.
Some questions lined up here. So let's get started. So rubber overmolding. Is there a general rule for minimum and maximum thickness?
Go ahead, Kyle.
Typically, I mean, depends on material. Typically, we say minimum is about 30 thousandths of an inch. Maximum, call it 150 thousandths, maybe 200 thousandths of an inch. give or take. Again, there's usually a good rule of thumb is 30 to 150, 100, 200,000.
Yeah. We
Yep.
also do offer some different processes as well to, in regards to rubber molding. So like, we're getting a lot more into LSR, which offers, thinner walls, as well as compression molding on the opposite side of that can offer a thicker wall section. So it really just depends on your part, the application, what properties you want, and the material itself.
Yeah, speaking of compression molding, I know we just published a post on compression molding, just helping understand. So versus injecting that liquid plastic in, compression is actually you're putting what's called a charge, but essentially a pre-treated or usually preheated like rubber material, and you're just kind of squishing it vertically in a tool cavity, and it's filling up that cavity and creating the shape. We actually did some compression molding for a recent featured case study on a company called Fever, where they had a TPU, so a thermoplastic urethane case that benefited from making it using that method versus traditional injection molding. So what's great is if you make the quote, send us the geometry that you want, and Kyra and Kyle are just absolutely awesome, and our entire injection molding team are awesome to look at this and critically evaluate what's going to be the best method and help you understand why, and we're going to try to direct you towards that the most successful option.
Awesome. And from a pricing standpoint, do you have a rough estimate for adding an undercut?
Again, a lot of that is going to depend on the part itself, but I would say it's going to range anywhere from maybe $500 for a straight simple hole, or it could really range up to several $1,000s. It depends on the requirement, but it's generally about $500 for a smaller hole.
And follow-up question, what if you have a second undercut on that same side?
If it's close enough to where it can all be captured at the same time, it would actually all be captured on the same hand load or same action.
Yeah, if it's on two separate sides of the parts, like maybe the same face, but two ends, it's going to be a little bit more difficult to capture that in one side action.
Yep.
So.
And just cosmetically, if you're looking at these, you'll see, so again, if you're looking, there's products around you right now that have these, a lot of times you'll see a side feature with kind of a square shape or, a rounded square shape around that. And that's actually the parting line or the shutoff area where that side action was making those undercut features while the rest of the material is molded around it.
Okay, awesome. And what about when turning 3D prints into injection molded parts? How do you make sure that the change doesn't have a negative effect on other parts in the assembly?
Yeah, so with that one, I mean, you just want to understand, your assembly way better than we do, and the application way better than we do. So ultimately, it comes down to, I would recommend doing another round of prototyping, just with the recommended changes for injection molding, making sure that those changes still work for your design and putting everything together. But ultimately, it depends on, the assembly, what tolerances and what clearance you've allowed for your parts. We're happy to take a look at it and walk through that with you, but ultimately it depends on how the part's designed.
Yeah, something we recommend pre-mold prototyping wise is usually stereolithography. So we have a bunch of different materials to simulate, everything from a kind of a flexible polypropylene up to rigid polycarbonate. But SLA tends to be the most accurate and reflective material for moving to the molding process. So we usually recommend at least a couple of SLA prints to check your design before moving the tooling. Kyra, I also wanted to bring up, because we're talking about like, will it work? So can you explain really quickly, when I say T1, like what's the on the mold side, like what's my expectation? What is a T1 shot, and what do we do after that?
Sure. So I'll talk a little bit about our process, once the sale or once the project is ordered. So basically what that looks like is we do assign a lead time to the quote. What that is it's initiated the day after your order processes with Zometry and is completed the day that your T1 samples are ready to ship to you. The T1 samples are actually the first 10 good parts off the tool that are shipped to you to confirm form, fit, and function of your product. Once you do approve those and you let us know, we allow for an additional 5 to 10 business days, depending on the quantity, to run and ship the remainder of your order. So that's what that looks like.
Yeah, so you could basically verify your mold design versus getting a box of 1,000 and finding out like something slightly off, because we can do a little bit of what's called grooming to the tool which can be a modification of a little bit of the design, or changing a core pin to make it a little bit bigger so the hole is bigger. Things like that we can do live and verify with those shots.
Okay, great. Here's a good one. Can you do mold flow analysis as part of the DFM process? That is when you're placing the gates and vents.
Go ahead, Kyle.
Kyra? Yes, the answer is yes. I mean, we do have mold flow. I mean, just keep in mind that mold flow is a simulation. There's a lot of other parameters that come into play that mold flow doesn't necessarily always cover. It's usually a good starting point, but a lot of it is really just that, a starting point to review parts.
Yeah, it gives you a good estimate on how things are going to fill out in regards to the correct gating location. So you can assign a gate there and inject, simulation and then you can also understand potential for warp and everything of that nature. But truly, you don't know exactly how the part is going to react until it's actually produced. So it gives us a good idea on what we should expect, but it could be, slightly off.
Okay, great. And with 4 more minutes officially till this webinar ends, I just want to let everyone know that, Kyra, Greg, and Kyle are available to email and ask your follow-up questions if we don't get to them. And we will be sending a webinar recording as well, so you can rewatch for any information you might have missed. So, Next question here. This is more like this is kind of a specific project question. So if you have 8 copies of a single piece, is it best to let Zometry handle the runner/gate placement, or is it something that you have to handle in the model?
Yeah, no, it's usually ideal to give us just the single design, because then we'll design the mold with the runner to keep it balanced, because there are a lot of considerations that are taken when designing that. We would design the runner and lay out.
I was going to say, to elaborate on that just a little bit more, the first 48 hours of that lead time that I mentioned before is dedicated to a formal DFM and PEG analysis, which is where we identify how the part is going to lay in the tool, the parting line strategy, ejection and gating strategy, and locations as well. So all of that is taken care of and is not proceeded to tool and kickoff without your sign off. So that will all be reviewed with you and you approve that.
Okay, let's do some quick and easy questions. Do we work with Canadian companies?
Yes.
Yes.
And do we assist with design development of a file into a 2D or CAD file?
Yeah, so I mean, I assist a lot of calls in regards to, you as the customer early on. I can definitely make recommendations. However, any changes will need to be made as you or from you as the customer right now. We currently aren't offering design engineering resources to where we can actually change the model. However, I can tell you, give you recommendations on what to do, and you can just send that right back to us. It's as simple as that.
Okay, back to, and then a capabilities question. What size range of capabilities do we offer? What's the highest tonnage injection molding machine we have?
Largest, which is over in Asia, is about a 2,000 ton press. Here in the US, we have about a 1,000 ton press. I think it's a 980 ton press. And it goes down to, well, with some micro molding machines, about 5 tons.
Okay.
Yeah, and just when we talk about tonnage, so I know because we're talking about some people who may be describing taking a 3D print. So tonnage is literally the clamping force of that tool that's required to inject that plastic at very, very high pressure. So when you have a 750 ton press, you're just able to accomplish that hold where you're injecting that material at extremely fast rates and extremely high pressure without it actually, breaking the tool or, squirting plastic out the side there. But also sometimes you have to run a higher tonnage press, even if the part is, it doesn't require a lot of material if it's a certain size, because tonnage also usually correlates with the size of the tool that you're making. So you may find that if you have a very, very, like say you have a 28-inch long belt, you may have to use a larger tonnage press, which has a little bit higher overhead just because the size of that tool that's required.
Okay. And what about family mold? family molds. So for example, for a low run, 100 to 200 products, can you create a family mold assuming parts are of similar dimensions? And does this
Yeah.
save costs?
Absolutely. So what we can do, we can absolutely do family tools. We try and partner parts together or family parts together that are in similar shape, size, and mass. So we want to be able to shoot the same amount of plastic into each cavity, and that's ideal with family tooling. So overall, Kyle, can you speak to the cost side a little bit?
Yeah, putting a family together, it's going to save anywhere from, call it 10 to 20% if you were to make two separate molds. Again, depends on the size and geometry. To carry on to what Kyra said a little bit, the other option is if there's parts that are maybe of different mass, different volume, you can actually have a run or shut off. So you can actually still run the parts independently, even though they're all in one tool.
Right.
Just wanted to ask a question to the team here. So what about if I have different materials? So I have a set of parts and they're different materials. Can I do a family tool with different materials?
Yes.
I would not recommend, but you can. But
I wouldn't recommend it. Yeah. Yes, you can. You would absolutely have to have the runner shut off to do that.
Yeah.
Okay, great. And we'll take a couple more questions here. So what about products with lettering? Are they less cost effective to mold?
It's very common for us to have some sort of text or lettering within the tool. Just something to note on that design aspect of it is the first off, good news is most tool shops are running EDMs. Where in CNC machining, EDM is like this. Oh, you have to add EDM. It's a separate operation. Most of our tool shops, EDM is how you get sharp corners and text and other features. So so it's much more integrated into the pricing tooling and much more common. Depending on the text size, it may be burnt into the tool. So if it's extruded text, it may be burnt into the tool using a EDM system. And if it can be milled, so if it is a larger text, that can often be used just with an engraving mill. So sometimes the text size can change pricing significantly, but as Kyra mentioned before, and Kyle's mentioned, we want you to give us the design that you want to have. Like we'll give you the feedback on what what will be what on it, but it is very, very common to add things like text and labeling and port labeling right within the mold itself.
Okay, and here's a materials question. We want to compare silicone with a TP that has a similar field. Do you have 3D printed TP with a similar field to carbon SIL30? Sorry if I butchered that.
Still 30, huh? Hey, look at that. Yeah. So yes, we can simulate. We can look at this, and with data sheets on materials, you should be able to look at durometer, which is the squish factor, and then that elongation before break, which is that stretch factor. And there's and some tensile strengths. So you can actually look at data sheets and help match that. And you guys have I know, Kyra, you all have a gigantic database that you're able to access as well, right?
Yeah, we definitely have subscriptions online to online materials databases where specifically if you're looking for a certain shore hardness, we can absolutely accommodate and find a material that's closely related to that in regards to the durometer and properties.
Okay, so let's do 2 more questions here before we wrap it up. So this one, this person has commented 30% a 30% depth group around a boss is an interesting tip. I previously learned that a fillet around a base of a boss adds strength. So do you simply have to choose between reinforcing and reducing seam?
So you can use this trick as well as put reinforcing ribs. So think like those rocket ship designs, like that kind of fin, that fin design actually helps reinforce without adding extra mass. Again, this is more of a sink reduction on cosmetic face tip. If you are putting those fins down, obviously like where the fin junctions on that little cuts, you still got to remain that solid because we can't do four little undercuts under on that feature there. But you can add stiffness in other ways and reinforce that feature. Fillets are always your friend, though. I will never say don't fill it, but just you can actually, instead of that sharp groove, you can actually kind of round it out. And I've seen even versions of this where it kind of steps down, moves, and goes back up to the boss. So there's definitely variations there.
Okay, great. And final question that kind of addresses these other questions. Do we have recommendations for sources for design help?
Kyra, but I was going to say we do have we do work with Zverse, which is a design on demand company, and we have some links. If you go to our FAQ, you can look at that. And what's nice about that is you're able to kind of down select what your needs are. So I have a design, but I want to make it manufacturable for this, or just going saying I have a napkin sketch and I want to ultimately make this many of this product. And you'll be able to get a quote through. So we're partnered with them, so they are able to work on those design efforts, and then you can get that file uploaded directly to Zometry site to start getting some quotes out. Like anything, prototyping is an iterative process. We have so many options. So when you are looking at injection mold, it's very likely that you're also going to be using selective laser sintering or HP multi-jet fusion for your initial runs and prototypes. There's even SLA for fit checks and much more accurate pre-mold designs. So a lot of times you do that 3D printing, prototyping, working your way up, and then you stop for a little bit while you're working on some moldability DFM, and then you run back to 3D printing for a very quick design validation before committing to the tool. So it's not always a cutoff point. A lot of times there's different reasons why I'm using 3D printing. So from initial production and then for fit check verification, you can use a lot of the same services that we have, and we have it all here.
Right, and in terms of getting started, we have a lot of resources on our blog, injection molding design guides, and we're always a phone call away. So with that, thank you all for joining us in this webinar. Please send any follow-up questions to us. I know our specialists here will also be following up. And thank you guys so much for sharing your expertise. Do you have any last things to say or share?
The only thing I would say, oh, sorry.
No, Kyra, go ahead. I was just going to put this up here because that's an awesome deal.
Yes,
yeah.
That is an awesome deal. And the only thing I would say too is everything that we spoke to, everything is specifically revolved around your design as well. So it could be adjusted, based on your design and as needed. But we're always happy to walk through that with you and support any questions you have. Like Serena said, we're always a phone call or an email away.
Awesome. Well, we will see you guys in the next one. Thank you so much and have a great day.
Great. Thank you all.
Thanks, everyone.